Okay, so here is lecture 3. Lecture 3. Oh, sorry. Is it? It's lecture 4. Lecture 4. Let me continue to talk about what I stopped last time, which was the integral test. Right? The integral test. Continue. The integral test. Continue. You probably see a problem in your homework that asks you to solve some problem like this. Problem. Show that the sum converges 1 over n, and then ln of n, and then you raise it to some power. In this case, it's square. Show that this converges. Converges. Any idea how we are going to use integral test here? What function should we pick? This is my an. Remember, this is my an. Someone say. Okay, we're gonna talk about getting refund later. Okay, now it's class time. Email me. I'll give you the link. Okay, this is my an. Right. How are we going to use the integral test to show it converges? Any idea? What function should I take?
1 over x times ln x and then square that.
X and then ln of x and then square that. Right. Basically, it's the same thing here, right? So that when you plug in n, they agree with it. Yeah, and it's not difficult to show that it satisfies the 4 condition that I mentioned before. Right? Satisfy the 4 condition. Remember what the 4 conditions are. It has to be positive, right? It has to be decreasing, it has to be continuous, and it has to agree with this. I might not say it in the correct order, but that's basically what it is. Okay, well, now you just have to show that you just have to show that this integral, right? Because it starts from 2, so now you have 2 here. 1 over x and then ln of x square dx converge, right? Converges. How are we going to solve this integral here? What technique should we use?
Use substitution.
Use substitution. What should we substitute it at?
U equals ln of x.
Ln of x. Okay, great. Yes. So now we see that du, the derivative of u is going to be 1 over x. Okay, this means that my du is equal to dx divided by x. Right? I multiply dx to that side. Okay, well, it means that this, yeah, 1 over x ln of x, and then you square dx Yeah, let me rewrite it a little bit. I'm gonna write it this way. They're the same thing, right? I just move x to this side. That's gonna be dx by divided by x is just gonna be du, right? And u is ln of x, so this is 1 over u squared, right? When x is equal to 2, right, we have ln of 2 here, so you have to change this number as well, right? And when x approaches infinity, ln of x or u of x gonna approach infinity as well. So now you integrate this, right? This one is easy because it's just ln of 2 infinity of u to the minus 2 du. Let's show that it's finite. It's some number. And then you are done with this question. I'm gonna let you try to solve for it. In the homework problem, it's any p. Yeah, this number here is any p greater than 1. But the idea is exactly the same thing. Okay, next, right, what I left last time was this theorem. It's called bow for the remainder. Suppose that the theorem says, suppose that you have a series an that is convergent, series of positive numbers. So everything here is positive. And let's call that it's a convergent series, right? And I say that it converges to the number s here, and it converges to s. Yeah, let me say n again. And f is a function that satisfy the four condition. Then I let Rn equal to s. This is my s limit minus Sn. Sn is my the n partial sum. So the sum minus the n partial sum, I call it Rn. Then it's satisfied. Then we have that Rn must be less than or equal to you integrate from n to infinity of fx dx, and greater than n plus 1. And when you integrate from n plus 1 to infinity of fx dx. Yeah, let me explain briefly why this is true. Okay, let's look at this diagram here. So this is my f, right? My fx. It satisfies the four conditions, right? It's positive, it's continuous, it's decreasing, right? It's going to look like this. and let's say it agree with my an. So this is, so let's say this is my my n term. So this is an. This is an plus 1. The term n plus 1. N plus 2. So it agree with each term like this. Here's my question for you. What is this region here? The sum of all of this region. Yeah, the sum of these rectangles here. Can anyone tell me what it is equal to? You can unmute yourself. And okay, let's look at the first one. Let's look at this rectangle here. What is the area of this rectangle? Can anyone tell me?
Integral
Okay, integral of which one?
of n minus 1 to n.
N minus 1 to n. Of what function?
Oh, n plus 1 to n.
You mean n to n plus 1?
Right.
Okay. N plus 1. Of which one? I'm looking at the rectangle. Yeah.
AN.
What did you say again? I heard someone say something.
The area is AN plus 1 for the first rectangle.
Okay, yeah. I think you got that right. So yeah, it actually doesn't involve the integral, right? Remember how we compute an area of a rectangle, the area of a rectangle? We multiply the width and the height, right? What is the width? It's 1. What is the height? It's an plus 1. So it's 1 times an plus 1. You see that? So the area of the first one is an plus 1. What about the area of the next one? It should be an plus 2 here. What would be the second one?
1 times an plus 2.
An plus 2, right? The width times the height, right? So it's an plus 2. Do you see that now? Do you see that each rectangle has area equal to that an, right? Whatever that it is at. Say if you are looking at the n plus 1 term, that area gonna be equal to an. Sorry, I said. Say if you look at the n plus 8 term, right? The area is going to be an plus 8, for example. Right? So now if I sum all of this area of the area of these rectangles, it's just going to be an plus 1 plus an plus 2 plus an plus 3 plus and so on, right? Do you see that it is Rn? Right? Is it clear why it is Rn?
I have a quick question.
Yeah.
Why is it 1 times an plus 1?
Yeah, this is the rectangle of the first one, the area of the first rectangle here. Right? 1 is the width here. Do you agree with me that the width is 1?
Oh, I see. Thank you.
And the height is an plus 1. Right? Yeah, and the same thing here. Now we see that this area is Rn. Okay. Tell me if you don't see that.
I have a question.
Yeah.
So, like, the image makes sense, but like, I'm still kind of confused about the equation. Like, why is it sandwiched between n+1 and then n? Like the
Which
two
one?
inter-
This inequality?
Yeah, like how does that relate exactly to the picture?
Yeah, we're gonna see how it's gonna relate that to
Okay.
that. Right now we're gonna sum this area. Right? Okay. Again, let's look at another picture here. It's actually the same picture, the same function. Yeah. I just want to write it, draw it twice. So this is my an, same as above, +1, an +2, and so on. And this is n, this is n +1, this is n +2, and so on. Here's a question for you. What is the area of this rectangle?
Should be 1 times an plus 1, correct?
+1, yes. It's an +1, right? What about this one? It's 1 times an +2, right? An +2. And you see that if I keep doing this, it's just gonna be so on. Keep doing. If I keep doing, then, well, if I add this area up, I'm gonna get Rn again. +1 plus an +2 plus dot, right? You see that I'm adding two different things, but they are actually equal to each other, right? They look different, right? Yeah, but here is the point of doing this. Let me use another color. Let's use this one. What is this region here? Can anyone tell me?
It's from n to infinity.
Right. This region is the integral of n, the integral of fx from n to infinity. Remember that integral is the area under the curve, right? That's how I get this. It's easy to see that the green area here, the green or yellow area here, I don't know how you call it, is greater than Rn, right? Greater than the sum of the area of this rectangle. You see that? That's how we get, that's how I get this side of inequality. Yeah. Okay, good. Now let's look at the bottom here. My question for you is, what is this region? Can anyone tell me? It's the integral of fx from where to where?
n +1 to infinity.
To infinity. Which one is greater, Rn or this integral?
Rn.
Rn, because it's, you see, it's over the, right, some area that, you know, it has some extra area above the graph, right? So you have Rn is greater than or equal to this. That's how we get this side of equation, right? It said Rn is greater than that inequality, that integral. Any question so far? Okay, we're gonna use this to estimate something. I'm sorry, are we recording it?
Yeah.
Okay. let me see. Okay, good. Now let's see problem. Estimate summation of 7 over n cubed n from 1 to infinity to be with n estimate to be with n 0.5 of its exact value. First of all, my question for you is, why does this series converges?
Because it just gets smaller and smaller and smaller.
Does it look like anything we have seen before?
Oh, the P series test.
The P series. It's just a multiple, right? It's 7 times the P series, right? Right. Yeah. Great. So yeah, we know it converges. We want to estimate its value within 0.5 of its exact value. We know it converges. We don't know what it converges to. So let's estimate that. What does it mean here? This question. This question means that you want to find the n partial sum Sn, right, such that minus 0.5. So yeah, the difference between the actual sum, I call it S, minus the n partial sum is within this range, right? Minus 0.5 less than or equal to 0.5. That's the same thing, right? Okay. Well, what is S minus Sn? We call it Rn, right? So we want to find Sn such that Rn lie within this interval here. Well, apply the previous theorem, then apply the previous theorem. To the function fx equal to 7 over x cubed, right? So we have that n plus 1 infinity. Yeah, let me write this. It's 7x to the minus 3. So 7x to the minus 3 dx less than or equal to Rn less than or equal to, you do n from n to infinity of this same function. Right. Okay, let's think about what this is. What is this thing here? An antiderivative of this is just 7x to the minus 2 over minus 2. Right? And then we plug in n and then compute when it approaches infinity. By the way, this is an when you see infinity like this, it's called an improper integral. Basically, you have to do this. You have to say this. You have to say a and then take limit a approaches infinity. But I abuse notation. I just write minus infinity. Sorry, I just put infinity here. They really mean the same thing. I'm just lazy to write limit. Okay. Well, what happened if I plug in infinity to this? Can anyone tell me?
Get smaller.
Smaller, right? Because yeah, let me rewrite this, right? It's equal to 7 divided by minus 2x squared, right? It's minus power. It's become the denominator now. Now when x get bigger and bigger, the bottom get bigger and bigger, so it go to 0, like you said. So it's equal to 0 minus, when you plug in x equal to 1, x equal to n, right? So it's 7 over minus 2 times n square. Okay. What is it? Minus, that's plus. So 7 over 2n square. Okay, good. Let's keep computing this. Then it's become this, right? Rn less than or equal to 7 over 2n square, right? We just compute that this is equal to this. Now when n is equal to n plus 1, it's just going to be this. 2n plus 1 square. Right? Instead of n, now it's n plus 1. I just plug in n plus 1 to here. Any questions so far? Okay. Let's find n that make Rn between 0.5 and minus 0.5, right? Remember that this is what we want to show. Okay. Well, when n is equal to 1, I plug this fraction into calculator, and I get that when n equal to 1, I get 1.8750 less than R1, right? The n is equal to 1, and 3.5. Does this one imply this? Is it true now? Can anyone tell me? It's not, right? Okay, when n is equal to 2, because 3.5 is still, greater than 0.5. Okay. Now, when I plug in 2 into here, I get 0.3889 less than or equal to R2 less than or equal to 0.8750. It's still not in this interval because 0.8 is still greater than this, 0.5. Let's keep doing. N is equal to 3, I plug it in here, I get 0.2188 less than R3 less than or equal to 0.3889. Is it in this interval now? Yes, right? Yes, so we found it. We found it. Found it. We found n that make it lie inside this interval.
I have a quick question.
Yes.
Is the only way of finding the right n is to plug it into a calculator?
Yes, I would say. Yeah.
Thank you.
I also have a question. Like for the left side, we're never getting negative 0.5. Does that matter?
It doesn't matter. Yeah. It just need to be in this interval. You just have to make sure that the inequality here lie in this interval. Yeah,
Okay, sure. Thank you.
Yeah, it never be negative this side because the function is positive. So the remainder, right? We call this thing the remainder, is always going to be positive. Yeah, but that doesn't make anything change. So yeah, we found n. Did I answer the question? Can anyone tell me?
No.
No.
No. What does the question ask? Ask me to estimate it, right? So what should I answer?
You answer a range.
I answer the range. What range? This range here?
Yes.
Actually, that's not quite what we should answer.
You have to sum up the three values, the first
Right.
three.
Right. We have to remember here. We want to find what? Sn, right? So our answer is S3. Our answer is S3. What is S3? Well, the first three terms, right? Sorry, 7 over 2 cube plus 7 over 3 cube. It turned out to be, yeah, let me just put equal 8.134. Yeah. Any question? Yeah, there is a homework problem that is similar to this. It's actually the same exact function, the exact same function, but I want you to estimate it closer than this. Okay. The idea is the same thing. So
I have a question.
yes,
So when you got the 8.134, you plugged into which equation exactly?
I compute this thing. I didn't put it in any other equation.
Okay.
Remember, S3 is the first three terms, right? The first three terms of this series. So I plug in the first term, I plug in 1, the second term I plug in 2, the third term I plug in 3. That's how I get S3 here. Okay, let's move on to another topic here. Now we get to another topic. It's 10.4. 10.4. The comparison test. Comparison test. Let me just say the theorem. How about that? Theorem. Yeah. The first big technique that we talk about is integral test, right? Now it's a second one. It's called comparison test. The first theorem called direct comparison test. Direct comparison test. It says if you have three sequences, AN, BN, CN of non-negative term, B non-negative, B sequences of non-negative. Negative term. Suppose that for some integer, capital letter N, yeah, for some N, Dn, should I call Dn? Okay, I should call Dn then. Yeah, let's call Dn. An, Cn, Dn. Dn is less than or equal to An, less than or equal to Cn. Suppose that this happened for all n greater than this number, greater than or equal to this number. The conclusion is then 1. If this series Cn converges. And so does An converges. The second result say that if Dn diverges, then so does An. So An diverges. Anyone want to explain briefly why this is true? This theorem is true? You can try to say it. It's okay if it's not correct. I want to hear what you think.
Maybe just because like if a series that is larger than something converges, then something that's smaller than it must also converge, just because like thinking about
Right? It's bounded by something, right? Is that what you're trying to say?
yeah.
It cannot go beyond something. Right? If this thing get to some number, then it's likely that this sum also get to some number, something like that.
Yeah.
Yeah. Okay, yeah, that's basically what it is. And a more precise idea of the proof is to use monotone convergent theorem. Idea of the proof is to use monotone convergent theorem. Monotone convergent theorem. Here is what important here. Non-negative. Every term has to be non-negative. But I'm not going to show you how to do this. You can think about this or look at the textbook of how to prove it. Let's get to problems. The proof is
Wait,
fairly easy. Oh, sorry. You have question?
yeah, I just wonder what's the relationship with the AN, CN, and DN? I'm kind of confused.
There are three different sequences.
Oh, okay, so
We have
they
three
are
different
related.
sequences. And suppose that this is correct. Suppose that Dn is less than or equal to An, and An is less than or equal to Cn. If this is true, then if this happens, then it converges. If this happens, then it diverges.
But if DN is diverges, so how can you compare which one's bigger, which one's smaller? I mean, if DN and AN are all diverges.
Oh, remember what a sequence look like? A sequence look like this, right? 1, 2, 3, 4, and let's say I call this thing Dn, right? This is my sequence Dn. This is D1, D2, D3, D4. And my An can look like this, 3, 4, 5, 6. Then Dn is less than An. Do you agree with me? D1
Yes.
is less than D2, A1. D2 is less than A2. So
Right.
it's possible to compare them. Yeah.
Oh, I see. Thank you.
Yeah.
I have a question too.
Yep.
So why does it have to be non-negative?
Yeah. The reason is that there are many things that make it wrong. Yeah. If it's non-negative, basically if it's non-negative, then each term can cancel each other. When it's non-negative, when you add things that are non-negative, it's just gonna get bigger. That's why you use the monotone convergent theorem. Right? Monotone means it's increasing. You see that? Yeah, that's the idea behind it. It need to be monotone. The partial sum need to be monotone.
Okay, I see. Thank you.
Right? If it's non-negative, you add non-negative thing again and again, it's just gonna get bigger and bigger. So it's monotone. Yeah.
What if it's like flipped? What if like Cn diverges and then Dn converges?
What if Dn converges?
Yeah, and then like what if Cn diverges?
That means you cannot use this comparison. It doesn't work. It doesn't tell you anything. Yeah, that's a good question. Yeah.
Okay, thank you.
See a question. So someone asked question. So monotone works for series too? Monotone convergence theorem is for series, is for sequences. But how do we prove that a series converges? Remember? We prove that a series converges if its partial sum converges. Right? So this is its partial sum. Its partial sum is a sequence. That's why we can use monotone convergence theorem. Okay, yeah, okay, good. Yeah, the language of series can be translated to the language of sequences because of the definition of convergent problem. Yeah, let's look at the first problem. Let me put it here. Does this converges? Does this converge? Any guess?
I think yeah.
You think yes? Anyone think it doesn't? Why do you think it converges?
Because the numerator is always between 0 and 1, and then the denominator, because of the p series.
Right. That's good observation. It looked kind of similar to P series when P is equal to 3/2. Is that what you are trying to say? Right. So yeah, that's a good observation. And the answer is yes, it converges. And I'm gonna show by using the above theorem. So I take Cn to be equal to 1 over n 3/2. Then because cosine of something square, right, is always less than or equal to 1. So if I divide both sides by n to the 3/2, right, both sides, then I have this inequality. But this inequality say that I call this an. So it means an is less than Cn, less than or equal to Cn. So this is my Cn. We know that Cn converges by P series. P is equal to 3/2, that's greater than 1. And because of this, so thus an converges. By the first result here, right? Here I'm using this one. Cn converges. So does AN. Any question about this? You see that I compare it to something that I know converges. How do I know to compare to this CN? Like someone just mentioned, it looks similar to this sequence here, each term. That's why I think about this one when I first see it.
So CN converges to 0 for.
It doesn't tell you what it converges to. Yeah.
So how do you know CN converges? Kind of confused. Because is it the P series thing where?
Which one? Which one converges? This
You
CN?
said CN converges, right?
Which one again? Sorry.
CN.
CN. Yeah, it converges because what is this sum here? 3/2. That's a P series, right?
Mm-hmm.
Yeah. What is P here?
3/2.
It's greater than 1, right?
Okay,
And
got it.
remember that if P is greater than 1, then it converges. Yeah, good question.
Which part is P?
P is the power here.
Oh, I see. Thank you.
Yeah, let me go back to that theorem, maybe. Where is it? We talk about it here, right? Here, the theorem say 1/n to the P converges if P is greater than 1 and diverges everything else. Okay, good. Let's do another one. Problem. Does this converge? 5/5n minus 1. Any guess?
No, it doesn't, because if you compare it to 5/5n, 5/5n doesn't converge, so this one shouldn't converge either.
Okay. Yeah, it looked like you're trying to say that it's kind of similar to 1/n, is that? Because you said 5/5 and it's.
Yeah.
Yeah. Okay. Yeah. That's actually correct. It diverges. And the way I'm gonna do is I take dn to be 1/n. Then I notice that an equal to 5/5n minus 1 is equal to 1/n minus 1/5. I divide both top and bottom by 5. Yeah. Certainly greater than 1/n, right? Because n is greater than this thing. 1 over something smaller is going to be greater than the other one. Yeah, it say that an is greater than or equal to dn because dn diverges. Dn, right, diverges. Why is that?
Power series.
What do you say again?
The P series.
It's
And
the P series, right? In particular, this is called harmonic series. Right? When P is equal to 1, there is a special name for it. Yeah, harmonic series diverges. So does that. Right, good. Any question? Yeah.
I have a question.
Yeah. Okay.
It's like when we are choosing another, DN or CN in order to compare? Do we need to show why the one we are chosen is also diverge or converge?
Right. You need to know the one that you want to compare with. Yeah.
So we don't need to write it on the paper, right?
Right.
I mean, if it's obvious to see, we don't need to write it to prove why the one we are chosen is diverge or converge.
You need to show why this diverges or why this converges. Here is what I show. Right? Oh yeah, I say it diverges because diverges by harmonic series. Harmonic.
Oh, okay. Yeah, get it.
I said, but I forgot to write it down. Yeah. Okay. Like this one, I give a reason. Right? It converges by P series, for example. Okay, good.
I have a question.
Yes.
So how do you know to choose a dn that's equal to 1 over n?
Yeah, that's a good question. In general, it can be difficult, but if you notice this, when in the long run, this thing is just going to be similar to 5 over 5n. Because that this minus 1, when n get bigger, just doesn't matter.
Okay, I see.
Right? But what is this? It's 1 over n. It kind of suggests me that this series is very similar to the harmonic series.
Mm-hmm.
Yeah.
Okay, I see. And another question where you have like 1 over n minus 1 over 5, I don't really see how it's greater than 1 over n.
Oh, do you agree that n minus 1 over 5 is greater than n? I mean, you minus something, you subtract n from something. Oh, sorry, it's the opposite. Do you agree with me this?
Yeah.
Yeah. Okay, so 1 over something smaller. This thing flip, right?
Okay, I see.
Yeah.
Thank
Because
you.
you divide by something smaller.
Mm-hmm.
That's how I get this. Okay, let's take a break here, and we will come back at around 3:10. If you have questions, you can ask me.